In thermodynamics, we are interested in converting heat into useful work. For that, we consider a system and its surroundings. The question now is how much quantity of heat can be converted into useful work? We will answer in this video. Consider a system at P1, T1 surrounded by atmosphere at pressure P, temperature T0. The initial state of the system at pressure P1 and temperature T1 is plotted on a PV diagram. If the system is allowed to expand, it performs work on the surroundings, loses heat to the surroundings, and reach equilibrium. During this expansion, the state of the system has changed from 1 to O, where the pressure is P0 and temperature is T0. What is this equilibrium with the surroundings? When a system is in equilibrium with its surroundings, we call that state as dead state. Beyond dead state, system cannot deliver work because the driving potential, temperature difference at equilibrium is equal to 0. System is at T0, surrounding is at T0, and hence the system cannot deliver any work once it reaches equilibrium state or the dead state. Apply first law of thermodynamics for the change of state. We get del Q minus del WS plus del WU is equal to change in the energy dV. What is this quantity del WS? It is the surrounding work. The system has to overcome the resistance offered by the atmosphere or the surroundings to the movement of the piston. So this is a work done by the surroundings on the system. Hence, negative sign. What is the quantity of this del WS? It's a work done to overcome surrounding resistance, and that is equal to P naught dV. P naught is the atmospheric pressure or the surrounding pressure, and dV is the change in volume of the system during the expansion process. Look at this quantity del Q. When the system expands, it rejects heat to the surroundings due to the temperature difference T1 and T naught. T1 is greater than T naught. Since there is a heat transfer, entropy is also transferred and entropy is also generated because of this heat transfer. This can be written as Ts, that is a change in entropy, is equal to del Q divided by T naught plus Ts generation, that is entropy generation. This equation can be rearranged like this. The first law equation we got for the system is shown here. Instead of the terms del Q and del WS, we can substitute the ones shown in red color and blue color. This equation can be rearranged like this. And to calculate W suffix U, we need to integrate the equation. And this integral equation can be rearranged like this. Upon integration, the quantity W suffix U is equal to E1 minus E naught minus T naught, S1 minus S naught plus T naught multiplied by entropy generated plus P naught into V1 minus V naught. What is V1? It is the initial state. What is the V naught? Final state. Why there is only one term in entropy generated? For that, consider the limits of integration. Initially, there is no entropy generated. Entropy is generated due to the heat transfer. So zeros for lower limit and entropy generated for the upper limit yields T naught is generated. So the lower limit 0. That's why we get only one term for entropy generated. What is this W suffix U? It is the useful work. Now we are going to define a term called exergy. What is this exergy? It is the maximum amount of useful work a system can deliver before it reaches equilibrium with its surrounding. That means before reaching the dead state. Denoted by the symbol X. Exergy X is equal to W suffix U. And look at this equation. What is this E1 minus E0? It is the summation of change in internal energy, change in kinetic energy, change in potential energy. Therefore, to identify how much work a system can deliver, we need to calculate the exergy of the system. Exergy is a property of the system, and it is an extensive property. We discussed a system can deliver maximum work when it reaches the dead state. Dead state is nothing but the equilibrium of the system with its surroundings. To calculate the maximum work a system can deliver, we need to find or estimate the quantity exergy. Practically, not all the systems are taken to the dead state during operation. Therefore, what is the useful work a system can deliver when it changes from state 1 to state 2? When the system is at state 1, it has got certain exergy. Exergy is the maximum work a system can deliver before it reaches equilibrium with its surroundings. Therefore, at 1, the system has got certain exergy. What is that exergy? Exergy, X suffix 1 is equal to change in energy minus T naught multiplied by change in entropy plus T naught multiplied by entropy generated plus P naught multiplied by change in volume. The subscript used here is E naught, S naught, V naught, not 2, meaning we assume the system has expanded from state 1 to the dead state. Therefore, V naught, T naught, T naught are the pressure, volume, and temperature of the surroundings. Now look at this state 2. The pressure is P2, temperature is T2. Therefore, it has not reached the equilibrium condition with its surroundings. The surrounding is at P naught, T naught. This implies the system at 2 is still capable of delivering work. In other words, it has got exergy. That exergy is equal to x suffix 2. Therefore, when a system undergoes a change of state from 1 to 2, exergy of the system changes. What is a change in exergy? Denoted by the symbol del x is equal to x2 minus x1, and that x2 minus x1 is shown here. And in this x2 minus x1 equation, we can cancel out the common terms, which yields del x is equal to E2 minus E1 minus T naught S2 minus S1 plus P naught V2 minus V1. Compare this equation with W suffix U. Remember, W suffix U is the maximum work a system can deliver before reaching dead state. So compare del x equation and W suffix U equation. From this we can write W suffix U is equal to del x plus T naught S generation. What this equation says is, when a system undergoes a change of state from 1 to 2, and if this 2 is not equal to the surrounding condition, then the maximum work the system can deliver is equal to change in its exergy plus T naught multiplied by entropy generation. Now we will define another term called irreversibility. It is the difference between reversible work and useful work, denoted by the symbol I is equal to W reversible minus W suffix U. What is the useful work? We already discussed. And what is this W suffix reversible? We will discuss. Before that, irreversibility is the wasted work potential or the lost opportunity to do work. What is this W reversible? It is the maximum work a system can deliver in a reversible process. For a reversible process, and if the system final state is equal to the dead state, then reversible work is equal to exergy. For a reversible process, if the final state is equal to the dead state, then a reversible work is equal to exergy. For work consuming devices, I is equal to W suffix U minus W suffix reversible. And this irreversibility I is always positive for real process, and for irreversible processes it is equal to 0. Before concluding, in this video we defined a new term called exergy, which is the maximum useful work a system can deliver before it reaches its dead state. The quality of energy can also be assessed using the term exergy.
Thank you.